You will not miss out on this opportunity. So starting recording and transcription, dismiss. There we go. And it's even transcribing what I'm saying. So now I have to cut back on using my profanity a little bit more. All right. So back over to the slides. Okay. So what is data science? It's a pretty new term, actually. Data science. This is something the concepts have been around for a long time. It's really at the end of the day, it's just a lot of math working with a lot of data to solve very pragmatic problems. That's it. So I was on the phone yesterday with a colleague who has her PhD from Stanford in astrophysics. And she was like, but and I was asking her, I was like, so what is your research focus areas? And she was like, well, I started out in astrobiology and then we kind of moved over into blah, blah, blah. She was like, but honestly, at the end of the day, it's data science. And it's like, it's funny to hear an astrophysicist say that, or try to explain what she does. And not just an astrophysicist, this is someone who did her PhD at Stanford in astrophysics, trying to justify what, in her perspective, was wasting time doing a PhD in astrophysics, because she's like, let me make it relevant. It's actually data science. So what data science is doing is taking a lot of the concepts that some of these more exotic, sexy sounding careers have done in the past, but that have been very focused on a few kind of problem sets, and saying, hey, the same stuff that you're using, for example, for predicting the impact of colliding atoms in nuclear fission, or the same thing that you're using for predicting stock market fluctuations, are the same maths that can be utilized across a number of different problems. And those maths can be used at scale, at really, really big scale, with a lot of data. So not just like 1 times series of cash flows and divide that by 1 plus the rate of exponent to the number to the end period, some of that together. But it can do this in billions and billions and trillions and gajillions to make up a number amounts of data. And so that's what data science is all about, is saying, let's use the math, let's use some computers to power that math, let's ingest a shit ton of data, and let's solve some problems. That's at the core what data science is all about. So why do you give a shit about data science? Why do you care? The reason you should care about data science is because data is at the core of every single business in the world, every single organization, every single problem that you're trying to solve in the world. Data is core to every single one of them. And the concepts that are being used, whether it's in nuclear fission, or whether it is in retail, or whether it is in automotive or manufacturing, logistics, whatever the case is, are pretty much the same at the very high level. So the same algorithms, the same type of tech stacks, the same types of ways of approaching the problem, with very minute differences, very, very detailed differences that shift from one problem to the next. And that's and so why should you care about it is because this is creating massive, unprecedented opportunities. We are at the beginning of this information age. We were shifting out of the industrialization age over into the information age. It started, it depends on who you talk to, 1980s, 1990s, early 2000s, depending on what part of the information age you want to consider. But as we move further into the information age, the data element is going to be more and more critical. We're starting to see that in order to do these things at scale, in order to do these things at scale, in order to have these type of multiple perspectives looking at similar problems and sharing those perspectives, it requires a lot of work, and a lot of opportunities are created for softwares to start up and solving this. So let's just kind of fly through some of the topics. And look, you stop me on any of these, and we can talk for the next hour on any one of these slides. I'm going to go through kind of fast, but here's what I promise you I will do. I will go back for each of these slides, and I will try to make a 3-minute video for each of them that will talk about. So if you kind of find yourself wandering off, or you're checking your email over here, or you're on your TikToks, not a huge issue. I'm going to do that for you because these concepts are, I know them, I can talk about them in my sleep, but they're probably completely brand new to you. And if I was, for example, taking a class on nuclear fission right now, And someone was like, we're just going to fly over the topics. I'm like, well, that sucks. I'm not going to get anything out of it. So I will go back and do this for you later this week because I have a holiday and I'll spend that time doing that. All right, so let's move. Well, when I get on the slides, let's move. And if the slide's big enough, can you see? All right, cool. So there's a lot of people who get involved in the data science process. Ultimately, it's you have lots of hardware, you have lots of software that are involved, but I and most of my friends are firm believers of humans over hardware. Ultimately, it comes down to people being able to do something with it. So who are those people and what are they doing? We have different folks. We have data engineers. We have domain experts. We have data analysts, software engineers, infrastructure architects, and system experts that are all kind of poking at the data science problems in different ways. Notice how data scientist is not mentioned on here, and I'll tell you why in a moment. These are all kind of critical enablers. If you think about the data scientist, this is the massive big brain person who's saying, okay, I have to think through, I have to understand your problem. Most of the time, it's a problem that hasn't really been solved uniquely in the way that you're wanting to solve it before. And I have to think through what is the math that could be used for solving that problem if we had all the data today. But before I can go say, well, what math problem could possibly be solved for that, I need to go talk to this person, the data engineer. And why do I need to talk to the data engineer? Because the data engineer is going to say, here, Justin, is the data that you have that you can use to solve this problem, or that we can acquire for you to solve this problem, or based on what we are going to be doing with our business, we will get that will let you solve this problem. If you don't have the data, you can't solve the problem. And if you remember, that's like right there, square at the center of the Venn diagram. Without data, there is no data scientist. You just have a scientist. All right. But then you need to have domain experts. So what is a domain expert? A domain expert could be, for example, it could be something like, let's take logistics. So it's one thing to have all the data on where all shipping containers are in the world, where all shipping routes are in the world, where everything is around the world. But if you don't really have someone who understands how all those pieces come together, who don't understand how DSV works, who understands how Maersk works, who understands why there's a backup and a port in Los Angeles, or who understands why we have these different stop points, what is going on at the Suez Canal, et cetera, that domain knowledge is kind of like everything else is the ingredients, but the domain knowledge is like the throwing the salt and the spices onto it in exactly the right way to make it actually come to life, right? It's the difference between recipe and a chef who can kind of bring it together. Business translators are kind of similar. These are people, we talk a lot of times with data engineers and data scientists, and it's really typical that when you talk to a data scientist, they're kind of like looking down at their shoes, and that's like the most eye contact you get with them. They're very introverted, very, very smart people. Same thing with data engineers for the most part. They don't spend a whole lot of time thinking, well, how am I going to tell the story with this data? How am I going to help visualize this as a part of a problem that then executive type people can grab it and go use it as a part of some organizational change, some institutional change, some actually building some new product, some solving some issue. So you got to have this. It's not like a person. If you go on Indeed.de, and you type in business translator, you're probably going to come up with someone who can speak French, Greek, and German, and they're translating. But it's an act of something that's being done. Data analysts, after the data engineer and the data scientists have come together and said, okay, we're going to do this model, and they figured out how they're going to do it with the software engineers and the machine learning engineers, and it's gone through this production process. Data analysts are the people who are going to say, okay, well, let's look at the output and let's see what the data is telling us. Is this model right? Is it decaying over time because things are changing? Do we need to go back and refactor code, or is it going too slow and we need to go back and consider? So they give a feedback loop to all these other people on what does the outcome look like, and is it looking like what we thought it would look like, and what possibly should we change so that the data scientists can do more things. Engineers in general are all about, so they're not like, most engineers I know are not, they're not the big dreamer in the sense of, I wanted to develop a new product in the world. What most of the engineers who are working on are saying, you have developed a prototype of what it is that you want to do. It makes sense from a product market fit. It makes sense from solving a problem, and it's cool. It's sexy. Now give it to me and let me make sure that I do it securely. Let me make sure that I can do it to where it's going to scale up to however big we want to scale it at. Let me make sure that the code is going to not need to be refactored because it's based on old technologies, et cetera, et cetera. That's what engineers do. They come in and they solve problems, and those types of problems they solve are typically optimization type problems. Infrastructure architects come in and say, okay, so the data engineer found the data scientist knows the problem they want to solve. We got a software engineer who wants to come in and write all this code. Now what? Well, now they need to have someone who's going to like take these Lego blocks and stack them on top together on terms of what do you need for storing the data? What do you need for serving the data? What do you need for networking the data? What software do you need to be able to wrap all that together? That's what infrastructure architects come in and basically do. They say, based on our enterprise, based on our budgets, based on our problems that we're trying to solve, based on blah, 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 here's the type of infrastructure that we need. And that can really go one of two ways. Either they build it their own, they go to a boss and say, hey, I need you to write a check for me for X millions of dollars so that I can buy all this stuff, put it into place, give me more money because I need to hire people to come in and manage it for us. Or they go the other way and they say, give me a credit card, I'm going to give it over to Amazon, and I'm going to let them kind of do a lot of the stuff for us. Usually one of those two ways. So the point is you have a lot of different types of rules that are typically involved in this world that are solving a lot of different types of problems. Now, it is basically a big difference between the science and the art, right? So on the scientific end of the spectrum, you have tons of data, complex problems, all the math, all the how are we going to think about this in a scientific, repeatable way? Scientific method meaning you solved a problem that you can repeatedly solve over and over again, doing pretty much the same steps, right? That's a scientific process. But there's the art side to it as well. And I see this all the time. You can have the greatest solutions to the world. You can have the clearest vision of what the problem is, how you want to solve it, what data you need, what software you need to layer on top of it, blah, 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 blah. All those things that you need to do, scientific. But then the company is like, yeah, I read an article on the flight home that said AI is bullshit, and I don't want to do that. And then what? What are you going to do? Well, guess what? Your culture is not one that's like leaning in this area because you have a gray-haired old white man executive who says, I read an article in Harvard Business Review where one person said that this is stupid. Or I sat next to a guy on a flight and he said that they've tried 3 AI projects and they all failed. So therefore it'll fail for you, right? Just because he sucks at executing on an idea doesn't mean that you're necessarily going to suck on executing on an idea. But the reality is that's the way that the culture typically works. And so you could have cultural issues. You could have governance issues where maybe you want to try something really exotic in medical space, but guess what? You just can't because there's regulatory hurdles. You can't get access to all the data. You can't combine the data from drug discovery with patient data to really map out how you could use machine learning to better predict protein structures that will bind drugs to specific smart problems, because regulatory law says you can't do it. There are issues with whose agenda is it? So inside companies, and I see this even inside our company, I may have a cool idea. Frederick may have a business. Let's say Frederick owns a business. It's bigger than mine. It's dying. And Justin comes in, and I have this really cool idea for my business, and I want to innovate on it. And I've got Bjorn, who's like, yeah, I have a really cool idea as well. And we all go over to Godswill and say, hey, Godswill, I know you have a budget this year for $10 million. Justin says he needs 9. Frederick says he needs 11, and Bjorn says he needs 15. So how are we going to go out and actually solve any of these problems? Well, then you get into this whole, what's your innovation agenda? So Godswill now has to come back and say, well, Frederick, can you do anything of yours for 5? Or Frederick, if you and Justin come together and you align, is there any way that you can share this project? And Frederick's like, well, technically we could, but in reality, I'm not going to, because I refuse to give over any credit of what we're going to be doing over to Justin's business unit. And meanwhile, Bjorn's like over in the background because he doesn't know how to do the politics of the organization, and he's just yelling at everybody because he doesn't have any budget and he can't get any innovation agenda going on. There's just lots of these like artistic sides of there's nothing on paper, but it's like the people element of a business that breaks down. There's also a side of this is the whole training and development, which we'll get to in a couple of slides later. But most companies that we meet on a regular basis just don't have the people who understand all of this. They're used to working, if it's a logistics company, they work in logistics. If it's automotive, they work in automotive. And they typically do not have the type of data scientist on staff at scale. And that whole team that we looked at up here to be able to actually take an idea and scale it into an operational status. I'm going to largely skip past this slide today, just because this slide alone could take easily 2 hours of us talking. But I will send it to you because I want you to have a chance to kind of look through. But let me really briefly tell you what you're looking at. It's the hype cycle. If you type in Gartner hype cycle, you will find the Gartner hype cycle for a number of different technologies. This is not just for data science and machine learning. You'll find it for you can find it for crypto and blockchain technologies. You can find it for everything. And basically, they have these buckets where they say there's an innovation trigger, there's a peak of inflated expectations, there's what they call the trough of disillusionment, sorry, and the slope of enlightenment and the plateau of productivity. So all this is saying, we got this really cool idea. This could be something huge. Oh, this is going to be amazing. This is going to be the best thing ever. Oh, well, there's all the reality sets in of how well this can actually work in reality to, oh, you know what? In reality, we could make this work if we fix this to, we've done pretty much everything we can do with this. All right, that's pretty much how every Gartner hype cycle looks like. But what you should do is go through on your own time and just kind of scan through some of these technologies. The ones that are going to be a little bit more relevant to you, especially as financial students, are going to be things in ML ops. So that is machine learning operations. And what that effectively means is how do you not just build machine learning models, but then how do you operationalize that? So if you go to work at a bank, if you go work, support a trading desk, and let's say you spend the next 6 months, 12 months learning machine learning and artificial intelligence, and you go apply to be a quant at a bank, and you come up with a really great idea, your great idea is going to sit on your laptop or in your little private instance unless you understand how to operationalize it at scale, right? So ML ops is going to be really important for you. Deep learning is going to be really important for you. We'll talk about what that is in a few moments. And then graph analytics is also probably going to be pretty important for you. Graph analytics is not about it's not about creating graphs. it's about graphing. So graphing is a mathematical concept of having nodes and edges, and how do you develop relationships among a massive amount of entities and make sense of them, which makes a lot of sense if you're looking at investments across portfolios, because you can construct portfolios based off of graph theory. Basically. All right. So data science has a lot of different topics, a lot of different aspect areas. Whenever someone talks about artificial intelligence and machine learning, first of all, artificial intelligence and machine learning are arguably, if you talk to many people, a subset of data science. If you talk to other people that say, well, artificial intelligence is any type of trying to train a computer to be able to predict, a next event, or trying to predict an outcome. Machine learning being a way that we can do that in a way that is going to recreate some type of reality. Data science is not just about AI and ML though. There's a lot of like we said earlier, the data preparation. There's a lot of just the modeling around what does the problem look like. If you think about AI and ML, actually, if you think about data science, on one end of the spectrum, it's take a whole bunch of data and do some math on it and try to figure out, well, what is some insight that I can get at this single point in time? But then when you look at the machine learning and artificial intelligence, is saying, okay, well, and based on that insight, how then can I take all the data that we use to model to get to this point, and how can I structure that in an algorithm that will train a computer over some short period of time to where it can learn and recreate some outcome on an ongoing basis? How can it operationalize it, that ML ops part? How can we operationalize that so that it can grow and become better and better at doing something on a regular basis? And all you see here inside these circles, all these are different types of techniques used for doing it. It's different types of mathematics, from Bayesian learning to nearest neighbor, k nearest neighbors, to decision trees, sensors, and as you kind of get further deeper into this, even within machine learning, you would have deep learning, and with deep learning, we should probably put a little circle down here at the bottom, where it's taking machine learning and doing it on a very multi-layered perspective. So on this, at the simplest end of the spectrum, you would have a very simple neural network. So we have a series of inputs. We run some models on those inputs to try to do some statistical analysis to say, what can we learn based on the data that you put in, and then what type of output will we get from it? Deep learning is taking the same concept and is running it through multiple. Sometimes it's not just 4 layers. This can sometimes be up to thousands, and I've even read an article about millions. Google uses millions of layers in their deep neural networks. Just think about that for a second. Millions of computational layers is going on. Like, how do you know what's going on? You don't. This is the point. You have no idea. So what does that input and output look like then? Like, what are we actually doing with it? Well, again, so the first part is old school, right? We're talking about basic input, basic output. One example of this type of a network was teaching a computer how to play chess or checkers. It started with checkers. Checkers is a pretty known game where you just kind of move pieces around on a board. You jump over each other. Chess, much more complex game where each piece has its own different kind of agenda. There are different strategies, and there are closer to best ways that you can play a game. So in the 1980s, 1990s, there was a machine learning network that basically went from neural networks to deep learning algorithms to train a chess engine to be able to beat the world's best chess player, Gary Kasparov, and it beat him like 3 times in a row. This is a computer beating the best chess player in the world, like just smashed him. And now it's not only that, but then you take the same types of concepts and you say, okay, well, how far can we push the limits on an ability of a computer to think through what does, based on some inputs of past. So it basically fed the computer all the past chess games. The computer learned how to play chess by going back and recreating all the past chess games, and it did this in like a day. And then it outcomes, to be the world's best chess player. It can also do this for the game Go. Go is a Chinese game that is much more difficult to play than, it's easy to play, very difficult to master. Same thing, Google created a deep learning algorithm that, and a team worked on this to play the best Go player in the world. And it wound up beating him, and the world was completely shocked. There are scientific articles written all about this. But the point is, okay, cool. So we can start out with this picture, and I'm the only American on the call, so I'm probably the only person who knows who this is. But his name is George Washington, first president of the United States. So we can start out with this picture, and then we kind of break down the problem little bit by little bit. So what's going on inside each of these layers? Well, whenever you take like a machine learning class, when you start getting into the math behind all of this, it's going to get into, first it's going to create a huge vector of this. So a picture is nothing more than a whole bunch of pixels. Everyone knows what a pixel is, right? I assume that most of you are shopping on a regular basis for high definition television, so you know that more pixels means like it's the tiniest little part of your screen that represents a color on some spectrum. Right. So what that first layer is basically doing is saying, let's get down to the smallest level of every single pixel in this picture, and let's identify what is the level, what color is that? What's the gradient on that? Let's map that out into some type of mathematical term. Let's put that into some type of data so we can compare all this. I'm not just saying blue versus green, but I'm saying a 6-digit character versus a 6-digit character. Okay. And then the next step of that is to say, well, let's look at patterns. Can we see that the gradient of this one little block is connected to the gradient of this little block, or it's not? And as it starts to do that, it starts to kind of chunk them together, as you see here on step 2. So step 1, just throw it out onto the table. Step 2, let's start to look for little tiny little patterns. Step 3, how can we start to develop to pull those patterns together even further? Step 4, here's where it starts to get really exotic. How can we start to identify features? So along the way, it's not just about saying, okay, you have these different layers and you just like, it's magic, and you just kind of feed it through. Each one of these layers that you're going to put in are going to have their own libraries. The libraries are basically, like, let's say I want to say, Frederick, I'm just picking on you all day. Frederick is wearing what kind of shirt? Anybody? Bjorn, what kind of shirt is he wearing? Just a styled shirt.
What do you mean? Like he's wearing a sweater?
He's wearing a sweater, or I would maybe say he's wearing a hoodie, right? And what color is it, God's will?
I'm not seeing Frederick.
You're not seeing Frederick. Vu, what color is his shirt? Blue. I think you said blue. So we're just gonna go blue. So we know that it's a sweater or a hoodie, and we know that it's blue. But how do we know that? We know that because over time we built up some storage, right? We built up some memory in our head of what blue looks like, of what a sweater looks like, of what a hoodie looks like. We know that this time of year that he would likely be wearing a sweater. So we know that it's probably not like cut off here and you just got like nothing else underneath. We know that we know these things because we have a library built up in our head. And you know what I'm saying because you have built up context based on what I'm talking about. And that is very similar to what's going on inside this model. So there are entire libraries of the mathematics. There are entire libraries of being able to import the data sets. There are entire libraries of being able to identify known features. And these libraries are growing over time, bigger and bigger and bigger. So you're able to solve more and more problems. So it's not just about being able to say, here's a picture, identify that the output is George. It's being able to do really cool things. So what are some of those cool things? Cool things can be, for example, driving a car, autonomous driving cars. So in old school way, we would say there's an input, a feature extraction of what is this, and there's gonna be a classification as a car or not a car. And if you've ever seen the TV show Silicon Valley, I'll send you guys a link to a video on this where a guy creates the worst possible version of this, and it's basically a hot dog or not hot dog, machine learning model. But deep learning is not just about being able to say that this is a car or not a car, but deep learning is about being able to say, I want to have multiple versions of this deep learning algorithm working on a car. And so what I want is to be able to do, back up here, I want to be able to have the robotics side of being able to steer a steering wheel. I want to be able to have the vision side of having 360 different cameras around the car that can identify things. I want to be able to have the language synthesis that can listen to what's going on with me in the car, and I can get feedback to and from the autonomous drive. I want to be able to have sensors that can take the inputs from the vision and they can work with robotics on the car. You will have no less than approximately 100 different deep learning algorithms working on a self-driving car. These are different projects that will each have probably another 100. You're talking about thousands and thousands of deep learning projects that are working on an autonomous driving car. And what's going on behind it is not just can I identify if this is a piece of paper floating across the street, or is it a child running across the street? If it's a piece of paper, you're just going to drive through it. If it's a child, your car should slam on brakes. It's not just about understanding based on your GPS and based on the mapping and based on the The sensor of where other cars are, because it knows based on where other phones are and where other smart driving cars are at, where it should drive to and not drive to. But it's being able to take all that and synthesize it together in a way that creates a holistic machine. That, at its core, is what deep learning is all about. And when you take a stop, just take a pause for a second and just let your mind stop being kind of blown around the craziness of what deep learning is. And you just look around your room and you think, holy shit, how many things in my room today are driven by artificial intelligence? How many things in my life are using deep learning, or how many things will be using deep learning and artificial intelligence? And that is where all this opportunity is creating from. This is why so much money is running after everybody who thinks that they have a solution to one of these problems. Time to switch over to the next cup. Okay. So this is kind of like, you're probably asking yourself, well, that's all cool, Justin. I'm pretty excited. I want to get on this. How do I get going? What are these models that I need to start sitting down and creating flashcards on and learning, that I need to sit down with a Jupyter notebook and start cracking through? Well, that's a really good question. So it really depends on what type of problem you're wanting to solve. So I have a few slides that we will talk through that, but let me just rearrange really fast on the fly. And first, let's split the world into two different types of problems that you may want to solve. The first type of problem is a supervised problem. The second type of problem is anybody? Exactly, unsupervised problem. So in a supervised problem, what we're basically going to do is say, we know what an outcome should look like, and we are going to feed some data into it, and I want you to optimize getting to the output that we want, or I want you to classify what the outcome should be like. So for example, maybe if we all had our monitors on, we would take a picture of the screen, feed it into a model, and it would come back and it would classify everyone here who's wearing dark clothing versus light colored clothing. Or maybe everyone who's wearing a hoodie versus everyone who is not wearing a hoodie. Or everyone who's wearing blue versus wearing not blue. Or something like, or into different, is that kind of like classification type of stuff. Regression, however, can look at things over periods of time. And it can look so we can look and say, over the first 15 minutes of the course, how many people came into the class? And how many people were late? And if we look at every class over time, was there one person who was consistently late? And over that time, can we look at that person and say, did that person come in with a Starbucks latte every time and say, sorry, they were stuck in a traffic jam? Over time, you start to develop that kind of a pattern, and you start to be able to regress back in time, and you can classify into the people who show up on time, and as well as to the group of people who are the assholes who stopped by Starbucks and then say that they were stuck in traffic and don't even have the common sense to drop their cup into the trash can on their way into a meeting. This happens all the time in calls, by the way. You'll go into a meeting and someone will be like, I'm so sorry, I got stuck in traffic. And they're like holding the Starbucks thing in their hand, and you're just like, bro, come on. All right, so that's on the supervised side. And so let me give a different analogy so that I can explain unsupervised. Supervised might be like, I show you a picture of a hockey player, and then I show you a picture of a golf player. And everyone on this call, even if you don't play golf, even if you don't play hockey, even if you don't really know what those two things are, after a couple of seconds of me telling you what those two things are, you could probably figure out, if I show you a new set of pictures, whether it's a golf player or whether it's a hockey player. They both stand pretty similar. They're both looking over a little small thing with a little stick, and they're going to hit it, right? Toward entirely different ends in an entirely different game, but that's basically the supervised side. Now let's look at the unsupervised side. Now I show you, I say, hey, machine learning algorithm, I want to know what the best golf swing in the world would look like. So what do? I take videos of myself playing golf, obviously, because I have a perfect golf swing. Just kidding. It's not perfect, but close. So I take videos of, for example, say Tiger Woods. take videos of whoever the great golf players are. I have 3 kids. It's been a very long time since I've played golf on any regular basis. So I take videos of the best golf players in the world. We kind of classify those because we can go back into our classification and we can say we know what the best players are, we know who the worst players are. So let's take those best players and let's put them over here into an unsupervised model. And now what I want to do is I want to back in this thing here, I want to take all of, okay, so first of all, simple neural network. We said we fed all the players in here and it went through whether they were good or bad, and it came out on the other side and it clustered us into whether they are a good golf player or bad golf player, right? So now we've got that group and we can put it into this part of the algorithm. And I know you're probably like, Justin, these are all just dots. Again, this is just a visual representation of the process. So we take all of our amazing best golf players in the world and we run their videos through a process. Very similar, very similar to what you saw down here. And what that video process is going to do is we're going to show it good and we're going to tell it it's good. And we're going to show it bad, and we're going to tell it that it's bad. And what it's going to do is it's going to take a video, which is nothing more than a whole bunch of pictures. And if anybody here's a photographer, you know, you can set your phone to like, 30 frames per second, 60 frames per second, 120, 240, whatever frames per second. That means it's taking 240 photos in 1 second when you do it in ultra slow motion, or if you're doing a time lapse, it's doing 1 photo every 5 minutes or 10 minutes or whatever the case is, right? But it all comes down to photos. And then it starts this exact same process. Take that photo, break it down, outcomes on the other side, some analysis of it, right? And it does that through linear algebra. It does that through some vector calculus. It does that with a lot of GPUs supporting it and some really fast, sexy analytics. But here's where it gets cool. So that we have this who's good, who's bad. We run it through this multiple hidden layers, all right? And what's going to come out on the other side is the end of the slide deck. What comes out on the other side of that is what should a perfect golf swing look like? And why can we use this? Let me tell you why we can use it. Now we take Justin, all right? Justin has a really good golf swing, but it's not perfect. So we can take a video of Justin. And by the way, I'm just completely making this up as I go, but I've used this with clients before, and they were like, this is 100% accurate to almost every type of these problems. We take a video of Justin, and we feed it through an algorithm. We feed it through the same video analysis back on the classification side, and it will predict whether or not I am a good or a bad golf player based on how well it knows that I can swing, based on how well it learned off of watching people who swing really well, based on how it learned off of people who can play well or not play well. Again, think about this. At the end of this, we take a video of Justin hitting a golf ball, one video. It goes back and compares the outcome of that at every single frame, or over a series of those frames, gets an average of my swing, and we'll go back and predict whether or not I will be good or bad. Now put golf to the side for a second, because I know none of you care about golf, right? Maybe one of you do, because you want to go into M&A, and that's kind of important. But let's put golf for a second. Can you imagine any instance where that might be applicable in finance? There is no wrong answer here, by the way. There's also no right answer, just answers.
I don't know, maybe with trading patterns or something like that.
Yes, credit patterns, 100%. So will someone go default on a loan, right? Whether it's, Justin wants to go buy a new Tesla Model X. Well, can Justin afford it with his own cash? Probably not. Can Justin afford it with credit? I could probably get the credit. Can Justin pay the credit back? We'll see. But let's run it through the algorithm. So we can, it's a great example. So we'll go through, we'll look at people who have similar income levels, similar savings, similar longevity in their jobs, et cetera, et cetera. This is on a personal finance side, right? We'll run through that whole model. Now we have a good classification system for being able to identify whether someone's good or bad. then we can run through similar models to say, let's predictively run through in the future what could look like if someone pays or doesn't pay off the payments. And what does that impact have on our capital structure and our ability, our working capital, right? Because if people over this percent are not paying on time, what does that have an impact on our ability to have enough capital in the bank to be able to pay off our credits, and blah, blah, blah. Great example. Other examples are maybe when you get into Bloomberg. Do you guys have Bloomberg at the, I'm pointing toward noting it over there. Do you have a Bloomberg terminal? Okay, so you get on Bloomberg terminal. What's one of the coolest things you can do on a Bloomberg terminal other than chat with people and look at jobs that are posted? One of the coolest things you can do is you can click on a company, you can find who all their suppliers are, right? That is a ton of exactly this. It's a ton of clusters of finding out, it's taking known information of who is applying into the company. You can take that, if you had that data in a good model, and you can put that all over to the side, and you could run prediction algorithms on what would happen if this supplier, for example, stopped existing. Back to that graph theory that I was talking about earlier when I said you should, you know, on the hype cycle, you should follow this graph area. On the graph, if you were to kill this one supplier, what would happen to Daimler? If you were to kill this one, because maybe that supplier gets all their components out of a country that is having import issues right now with the EU. Or maybe what happens if this stock in my portfolio is downgraded? Well, why would it be downgraded? Maybe because it's very reliant on semiconductors, and semiconductors are having a shortage all around the world. Or what happens if semiconductors have a shortage around the world? How can we go back and predict which stocks will have the most negative impact, and how will that affect the overall portfolio that we have, right? So there's a lot of different ways that this can play out. All right. And to do that, you have a lot of different models that you can use. You have classification, clustering, regression, and dimensionality reduction. You saw this on the previous slide as well. And it all comes down to kind of like, what do you want to do? And how much data do you have to do with it? And what is your ultimate outcome that you're hoping to achieve? This slide is not going to speak a whole lot to you, but this one probably will. This is from Microsoft, from Azure. Azure is essentially Microsoft's public cloud offering. Public cloud, just as a reminder, is nothing more than other companies building up compute infrastructures that you are able to rent effectively for your own uses. But it's not just their infrastructure. They also provide a lot of the stuff that you need to work on that infrastructure and make it make sense, which we'll talk a lot more about in the next slides. So this is a great thing. We're not going to obviously go through this slide today, but this is going to be a great resource for you. It starts with, what do you want to do? I want to extract information from text. Okay, so why would we maybe want to extract information from text? Maybe one of you are sitting around, you're like, you know what? I really like to get the insights from annual reports, but I would rather shoot myself in the head than sit down and read someone's annual report on a regular basis. Well, guess what? There's natural language processing that you can use for extracting insights from text. Maybe it's not something like that, but maybe and there's actually a company that does exactly that. They scan through entire annual reports and they come up with analysis like within seconds. Maybe it's doing Twitter sentiment. So you create an algorithm that's going to go and extract tons of information from Twitter around a company. So every time that company has a $sign and say for us HPE, and you see the sentiment is positive or negative, whether that's about the product or the stock or what's the general sentiment. Those are the types of things you can do. So anyway, long story short, what do you want to do? There's a lot of different ways you can do it. But what's interesting that I found in some of the talks I've had, especially in the last few weeks, is how much you see these over and over and over again. So we were talking with a group. It was a professor from Davidson College and a professor from MIT. Was that this week? No, this is the beginning of the week. Last week, we had a call where we were talking with them about nuclear physics and AI's uses in nuclear fission, and how what they're doing at places like CERN, where they're smashing atoms together and they're trying to predict what will happen when you smash the atoms together. and they smash some atoms together, and they see how close that prediction model was to it. Why that's important is because it helps to understand whether the models make sense, and when those models make sense, you can apply them to other things. Similar predictive models, this is a totally wildly different example. I was on a call with a guy from the World Economic Forum, and he said, look, one of the people who comes to our forum in Davos was looking at how can we get the best beer, how can we predict which beer is the best tasting beer with which food? And then how can we predict which foods people will want to eat at a restaurant, or that they'll want to consume around times of the year, et cetera, so that we can optimize our beer production and our beer distribution to the right places and recommend those as the best pairings with the foods based on levels of salt, based on the levels of acidity in the foods, all these different kind of things. What was interesting about that one, it was a similar issue we talked about earlier, the science and art. So that's kind of like the science of how both of those sides work. But let's talk about the art. Well, the art side is if you're working on the nuclear fission side and you are at Princeton University, now you have to find a way to get the colleagues in Korea at a different university to share data with you and to share your models together. If you're talking about on getting beer and food pairings, well, guess what? Beer companies have the beer data, and restaurants and grocery stores have all the food data, but neither side has both data. So how do you get both sides to share that data? How do you get them to talk to each other? So a lot of this, you can say, well, what do I want to do? How do I want to do it? And you can scientifically have the best solution in the world, but a lot of times it will come back down to that art that I was mentioning earlier of how are you actually going to do it. Humans over hardware, like I said. You have to have someone with a permanent smile and a fetching beard who can get on and just excite people to want to give over their data. All right, moving on. So the bad news is that there is a lot of math behind this. Lots and lots and lots of math. The good news is two things. Number one, you guys are all finance students, so you don't get scared by stuff like this. You get excited. You wake up in the morning and you're just like, man, I don't just want to see formulas, I want to see proofs of those formulas. And I love that about you. That's amazing. The even better news, however, is you don't have to know any of it. So there's a lot of people who have already thought through these problems and are thinking through these problems on a regular basis. And if there's one thing I can tell you with absolute 100,000% certainty is that programmers and developers and engineers are the laziest people in the world. They love to get things done in the most efficient way possible. Like I said earlier, engineers are all around optimization, right? And every developer I work with is like, show me the shortest line between point A and B. They're the same way as sales in that sense. They're always trying to find the easiest way to get something done. And the easiest way to get something done is, like I said earlier, building out those libraries, building up those dependencies. So how do we know that Frederick's shirt was blue? How do we know that he's wearing a hoodie? How do we know that, et cetera, et cetera? The way you teach these platforms is being able to have these types of dependencies to be able to work with. So, and again, you're probably like, well, that's great, but all you're showing me is a whole bunch of logos for things I have no idea what I'm looking at. Python's a snake, right? By the way, Python, if you're going to pick a programming language, if anyone here is interested in getting into programming, start with Python. The reason why I'm saying start with Python is because it is growing like crazy. It is really, really, really easy to get started with and use compared to, say, Java, compared to C++, for example, which have their own reasons for use. They are C++ is very optimized, it's very fast. Java can be used everywhere, but Python is becoming more and more applicable and useful across any number of problem sets, and it has a growing level of libraries that no other programming language has, and you can get started with it for free. Like you can go right now, while we're still talking, into your command line and import Python to your computer, and by the end of this call, you will have Python, or even better, you can go to Google Colab and just start programming in Python right there. And you don't even have to tell it you're programming in Python. You'll just figure it out that you're coding in Python because it's pretty smart. So you have all these different things that you're going to be using, and you're like, okay, well, cool. What are these libraries and what are they useful for? This is a super high-level sketch view. There are great tables. If you type in Google image data science library table, type that in. We can do it at the end of the call. You'll find great examples of this. In almost every research paper where someone's been solving some big problem, they will put their list of what their stack was that they used at the end of it. It's a really, really good way to cheat, because then what you can do is when you go into a job interview, you can say, well, I can see what you guys are probably trying to solve here. And based on the study that Markowitz and Apostolus did in 2019, there was we found that blah blah blah, and I know that they were also using blah blah blah, and I know that based on what I've seen on your job sites, your engineers must be also be using. Is that all pretty much correct? And suddenly the interviewer was like, whoa, who is this guy? Get out of my head, right? Because now you know everything about their company, you know everything about their tech stack, and you look like a complete Harry Potter genius, even though you're maybe not in Gryffindor. All right, so each of those kind of can get split up into different problem areas. So you have on the one end of the spectrum, this is your left side, right? Is this left or is this your right? Which one's left? Okay, so on the left side of the spectrum, you have your data, right? So getting your data together, like I said, way back, in a previous life, is all about the data engineer's problem. So the data scientist is saying, hey, look, here's my idea. Here's the problem that we're trying to solve. Here's how I think we can solve it. Data engineer is going to say, okay, cool. I'm going to go look at your data, and I'm going to go try to figure out, where does that data exist? Is this something that we have on premise? So we have it like actually in a computer somewhere on our own disks, or is this somewhere that's stored in the cloud? And what type of storage file is it? So accessing different types of files requires different types of methodologies, and that's all going to have different implications to the data engineer's ability to build this solution. The workflows. So how are we going to get the data? How is it going to stream it? How is it going to process it to the database? Well, how are we going to then take all that data, and now we've done something. We pulled it out, we played around with it a little bit, and we want to put it into something new. Well, what's that database going to look like? This, by the way, just as a total side note, this little elephant, I'll give a bonus point. I'll give a 1 to anyone in the class right now, if anyone can tell me what the name of this elephant is. Its name is Hadoop. So Hadoop is bought by Hortonworks, which is now owned by Cloudera, but Hadoop is the name. This was a developer who his son's favorite little toy was this little stuffed elephant, a little yellow elephant. And so he developed this thing on the side and named it Hadoop after his son's, or maybe it's his daughter's, his child's favorite toy. All right, so you got database. Like so we pulled it out, played with it. Now we need to have some way to store it. And there are different types of databases. There are different things software that's going to go on inside the database. To then the labeling to say, okay, well, when we say labeling, so we may have a data set that says golfers. We have a data set that says golfers with good swing, or we have a data set that says golfers pro, golfers with blah, 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 right? Back to our little golfing analogy. So how are we labeling the data, and how we label that data, and how can we label the data really is going to be integral to how we're going to be able to use that data. Because if we don't have it labeled correctly, guess what? Those little pictures you saw at the bottom of the screen earlier, can't do it, right? You won't be able to. You'll be able to feed that back together. You won't be able to, in the case of our autonomous driving car, get all those thousands and thousands of parallel processing algorithms to work together if they aren't labeled correctly and the data can't talk to each other, right? Through all these databases, through workflows and storage and blah blah blah. All right. So now we get over to the development side of things, and developing and training. So here is all about we've got the data in place. Now we need to actually build the thing that we're going to do. And so this up here, for example, you have your frameworks that you're going to be using. For example, this T is TensorFlow. Google bought that, and because it's a really fast version of processing these types of algorithms. PyTorch was developed by a guy who was actually a former Navy guy. He tried to become a Navy SEAL, He got injured during that training, went back and became an AI researcher, totally on the side. Stumbled his way into doing his PhD in artificial intelligence, founded PyTorch, and now has founded a group called Grid.ai. So now he has a startup that all evolved around him solving one problem on this whole big stack here. Yeah, it's pretty. I only know that because I was just reading about Grid.ai the other day because someone reached out about a role that they had. So you have the software engineer side. So again, Python. And by the way, Python is not a snake. Python comes from Monty Python, The Search for the Holy Grail, Monty Python, Life of Brian. It comes from the Monty Python series. That's where Python comes from. The people who wrote it had a sense of humor. That just happens to be that you also see it with a snake. So how are you going to develop this? Jupyter Notebooks is effectively a way that you start, is a way that you can go on a web and write your code and share it with other people. Git and GitHub is how I can collaborate with all of you. Maybe I start writing some code and I say, hey, Bjorn, can you check this out? I share it over with Bjorn. Bjorn's like, that's awesome. Then Vu and Frederick were like, hey, that thing that Bjorn and Justin were working on, it's pretty neat. We're going to fork that off and we're going to start working on our own little project. And Apostolist comes in and he's like, hey, wait a minute, that thing that they did over there was bullshit. I'm going to request that we pull that back. And meanwhile, Teodora is coming in and she's like, I'm just going to start writing some comments on everything. And so GitHub is about that collaboration around the software development environment. Resources are to say, okay, well that's groovy. We're gonna write some code. We're gonna put it together. We're gonna share it with everybody. And now we got to figure out how to get it to work across a whole bunch of different places. So remember all those libraries, those dependencies that we said earlier. This little thing right here, this little whale. Anybody know what that is? Docker. It stands for Docker containers. And this one little over here. So this looks like a shipping container, right? So what that is up there, it looks kind of like a ship, but it's a big whale. This one over here is a steering wheel. It's called Kubernetes. It comes from a Greek word, Apostolus and Theodora. So Kubernetes and Docker work together. I'm just going to talk about these two, for example, to say Docker is creating a container. A container is putting all of those dependencies, all those libraries, for example, everything you need to make this application work is putting it inside this one file. That's what a container is. So that way, when we get onto the call, if I uploaded to this call a clothing container, then Bjorn would have said, oh, hoodie. And I would have said, oh, hoodie. And Apostles would have said, oh, hoodie, when we all talked about Frederick's, because we all had the same library. We all had the same dependencies. And when you're looking at machine learning algorithms, that's really, really important. Because everywhere, whenever you write code, it's not just sitting on your laptop. It's not just like going out to some computer. Everywhere where it runs, it has to have all that library has to go with it. All those dependencies, everything that's going to work with it has to go with it. So what containers do is basically a file that you can put with that computer program wherever it's deployed that carries all the luggage that it needs to be able to do whatever it needs to do. And what Kubernetes does is it says, as much as you want to expand or contract those containers, as many containers as you want to put on that ship, we're going to help you orchestrate that, but better yet, we're going to automate it. And Google basically created that to allow the scale of your application to be able to grow as big and as small as it needs to be, and be able to be deployed as far and as close as it should be, right? So that's all about the scale of your software. And that ties directly to the scale of your ability to take your app, your idea, your solution to the world, which has the direct impacts on your, who left? We're getting to the good stuff. Someone with SS left, shame on them. All right, whoever that is, you all tell them I said shame. Did we have a lot of people dropped? Are we out of time? I thought we had from 10 to 11:30, no? Okay, well, whatever. I'm going to keep going. If you guys need to drop. I'm recording it. And if you're watching this later, shame on you. All right. So the point is, you got all this development and the training that's kind of going into this process. Then you got to deploy it. All right. So how are you actually going to get that TikTok onto your phone? How are you going to get maybe not a consumer-oriented application, but how are you going to get something that's maybe enterprise where it's called a microservices, solving one little problem, and you want to deploy it across the world so that, for example, in your Mercedes, you are able to have this engine check service that's running in the background continuously all the time. How can you make sure that that gets deployed? And there's just a whole lot of stuff that goes into doing this, whether it's going to be web-based, whether it's going to be Internet of Things, so out on some edge device-based. And there's a lot of work that goes into this thing called CI/CD, which is basically the continuous improvement, continuous development. Instead of us building something today and we ship it out and we wait and see what the feedback is, we ship part of it now and you give us some feedback, and then we kind of go back and we change things, and we kind of continuously move forward and code versus like pulling the whole thing back and sending it back out to the world. There's a lot of technologies, obviously, that kind of go into this space. All right.
I have a question for the technologies.
Yes, Apostolos, please.
Why is that so much? I mean, like, if I want to get into this this coding stuff, do I really have to learn like everything, or I mean, it's work enough to know what program is for what, but why are there so many different approaches for different
It's a great question. It's a really, really, really good question. I'm going to give you the unofficial and the official answer. All right. The unofficial answer is because the more that this stuff is broken up, the more that people who know this have built up a defense mechanism for their own job, right? If you understand all of this, this is a lot. First of all, let me be very clear. I know people who their entire job is just focusing on this one little part. For example, on doing S3, so the storing stable data, or people who are focused. I had a former neighbor, his entire job was running the Hadoop clusters for Daimler Finance, right? And like, these are massively complex. Each of them, you can spend an entire career on just learning those. People who understand the whole thing typically are more at the executive level and just basically needing to understand their overall landscape. They own budgets, they own teams of teams, and they have to understand how those teams are coming together to solve some enterprise level problem. They don't need to understand how to deploy, for example, a Hadoop cluster. They don't need to understand really anything about databases, other than that databases are really important. And what are the trade-off considerations for this versus that one, which the people who are working on there will come and present it. That being said, anytime you start specializing in the world, it's the same thing as like athletics. You start general and go specific. So when I train generally. For example, with cycling, I'm going to get out onto the bike and I'm just going to log miles for the first in any training period. It's just you should get time in the saddle, spend time doing that. And then as I go further, I'm going to spend specific times on climbs, specific times on sprints, specific times on doing long rides, specific times on recovery, specific times on things that enable all that. And it's very similar to this. As you start out, you would, for example, just start out with Python, just to understand, well, how do I import a library? And which library should I import? And how do I know which library I should import? And the way you're going to know that is you're going to go to a website. This is where everybody, there's a famous picture of a guy graduating with his computer science degree, and on the top of his hat it said, thanks Stacker Overflow. And because people go there and they'll post their questions, and it's a great repository to find where other people are having similar issues, and engineers, there's a lot of like TikTok and YouTube videos that make fun of this, because people basically go there and they copy all the code. It'll show like what computer science looks like in real life, and it's like you learn all these and you're like sitting down coding and what it is in reality, and you go to Google search thing, find Stacker Overflow article, copy, paste over into your code set, and look like a ninja, right? And that's so the reality is that not everybody knows all this, is what my point with that story is. A lot of people are bullshitting around on a lot of this. But starting with that basics, like with the cycling analogy, start with Python, learning the basics of computer programming, learning the basics of data science, and finding some guided courses that will say, and here are the dependencies that you need. You won't need all this, because you're not going to be scaling as a one person. an entire stack at enterprise level scale. You're not going to recreate Bosch. You may be wanting to create one web application that just needs to get some data, and you're going to have some user data, and you're going to present some visualization of data, watches, for example, to the end customer. And as they're kind of shopping, you want to learn more about them. And as you learn more about them, you want to predict what they're going to be doing or not doing. And as they're doing things, you want to see whether you were right or wrong. And so that is a lot simpler, and you can start off with the basics. And then as you kind of progress further, assuming that no one here is going to become a technologist in one of these areas, you can naturally see, based on your outcome, what it is you're trying to achieve. Like it said up here, what do you want to actually do? What it is that you actually need to know. And that's going to be your starting point. Like, what do you actually want to do? And it'll tell you what you need to be driving toward. And as you drive toward that, it'll tell you which of these libraries are making the most sense. Apostle, does that answer your question, or does that just completely run around circles around your question?
Yeah, I'm satisfied with the answer.
Okay. I'm smart enough to know that means I don't want you to go further. So, all right, cool. So now you've got all this like kind of software. You've got all these different things going on in place. What does that kind of look like from an enterprise perspective? And this is kind of getting technical stuff. So I'm gonna again just kind of like skip over the wave tops because I don't want you to leave a bad review on Yelp because I went into technical stuff. But long story short, you have IT and platforms where think about inside the company, right? So we may do some data science stuff inside the company on predicting when people are going to be sick, but they're not actually sick. Maybe predicting when sales reps are at their most optimal levels or not optimal levels. So you have IT sides, you have customer experience platforms. So how are we actually dealing with the customer? Where are they having problems? Where are they getting the solutions at? How satisfied or not satisfied are they? Ecosystem platforms. So a lot of times you will be working together with partners, and those partners are going to be able to create a network effects of your business. And so, but it can only create a network effect, which means that the value goes up as more people are working together on doing it. This goes back to Porter's 5 forces. That can only happen if all those partners are able to work together. If you have this ecosystem in place, you have a platform in place that will allow them to do that. And ultimately, IoT, anybody know what IoT stands for? Gives me a chance to sip the last bit of my coffee. IoT? Frederick is like Google.
Internet of Things.
Very well done. Your Google's faster than Frederick's. So IoT, Internet of Things. So it's being able to collect data out on some edge. Now this could be as simple as in my garden, I put down a little sensor into the ground that says how much of my what's the water level in around different plants, and it sends a signal back to some hub that sends a signal to a water supply that then provides water that then creates a circuitous loop, right? It could be something as simple as that. Could be something like oil wells. It could be something like Internet of Things on the cars, sensors on the cars. It could be not just things like my watch. It could also or like the Peloton, where it's kind of tracking when I ride the bike, when I don't ride the bike. It could be branch offices, so branches of coffee shops, branches of banks, et cetera, et cetera. Is that getting out into the closest edge that you can get to where the event is taking place, right? Is as close as you can get to where the data originates. And in the past, sometimes when you have that data, it is a few steps after the event taking place. And I'll give you an example, a retail store. So we may have a ton of data around when people shop. We know that in the month of December is the false economy, right? Most retail establishments make all of their money. They make like 90% of their income for the year in 1 month of the year. So if there's no Christmas time period, then 90% of the money isn't spent, and therefore, or it's spread out throughout the rest of the year, right? And so that can have a huge outsized impact. So we would know that because we have the data that started at the cash register, at the point of sale, the POS device. But what happened before the POS device? So an Internet of Things example would be having sensors inside of the stores that say, well, how many people are coming in at different times of day? Where do they walk around at? Where do they stop at? Where do they walk really fast through because they're cutting through to get to the food court faster? Or where do they go because they're trying to get to the restroom faster? And based on all that kind of information, and based on when people are buying and what they're buying, can we put things there? Can we put, hey, there's a sale. You know, you're on your way to pee, but we can let you know that there's also a sale on say gloves because it's October and oh, I need gloves. Or we can say, have you forgotten your wife's Christmas present? And you can put a discount for something at Tiffany's, and it just happens to be on the way to you know, the men's skiing section or whatever. So that's what I mean. It's like getting closer and closer to the event that takes place and being able to predict and be able to influence the outcomes better and better. So anyway, long story short is that you need this platform. You have to consider each of these, like, what is it you're trying to achieve? What is it the companies you're looking at are trying to achieve? And so going back to the previous slide, each of these are trying to solve a technical problem. These are massive, massive, huge technical problems. And there are companies across this landscape that you'll be looking at as you know, companies that maybe you want to pretend are your startup. Inside here, the question is, well, how do those companies then solve the types of problems that we're trying to solve? Is it solving internal, a customer, an ecosystem, or an Internet of Things type of problem? Okay. This one will really kill you, but let me just make the long story short that Amazon, one of Amazon's biggest businesses is not making sure that you get all the things that you want, that you got. You go on Amazon.de, you one-click buy, you're a Prime member, and so it shows up on your doorstep that afternoon. I have an entire business called Amazon Web Services. It started about 15 years ago by the guy who just got announced to be the new CEO of Amazon, Andy something. And effectively what this was Amazon's play to take on the entire computing infrastructure market. And Amazon is by far the biggest player in this market. Actually, Microsoft may be taking over them right now, but you have three big players that do public cloud. So all these things that I was talking about earlier, to your question, Apostolos, you know, why would I have to know all this? Or why do I have to put all this in place? What kind of infrastructure do I have to be able to put in place? Do I have to build, compute, store, networking, and blah, blah, blah? You don't. And here's why. As long as you have a credit card, you can get an Amazon Web Services account, and you can set up your entire end-to-end infrastructure with AWS. It is that simple. It's as simple as having a credit card and getting started, maybe hiring in a couple of people off of Fiverr, Fiverr.com. These are basically freelance people who know how to do each of these different areas. You know what needs to be done. You hire them in. They can help set up your storage. They help you set up your databases. They help you set up blah, blah, blah. And now you've got a whole system in place. And you pay on an as-you-go basis with Amazon. Same thing with Google. Google's much smaller than Amazon, but they have a thing called Google Cloud Partners, GCP. Google Cloud Platform, GCP. Same thing with Microsoft, called Microsoft Azure, as we mentioned earlier on slide 31. And Azure is growing really, really fast because where Amazon can do everything, and they have an almost unlimited amount of things that they provide as a service that you can pick and choose from. It's like kind of going down a buffet line of different IT options that you can choose from that you would need for whatever it is that you're trying to do, whether we're creating an artificial intelligence driven beer, or whether it is that we are trying to develop a new drug, right? Or we want to discover a new drug. Everything in between is being done on these types of systems. And so what Microsoft does, just as a side note, what's interesting is they have the largest enterprise instance of or footprint of software in the world, right? Because everyone runs on Microsoft Office, everyone runs on. It started with Word, Outlook, PowerPoint, Excel, etc. And then on top of that, they started linking it all together with Teams. They started linking it together like we're on right now. They started linking it together with SharePoint, and it started tying overall organizations together with their software. So it's not just that I use Excel, but now I use Excel as a part of my day-to-day workflow that Microsoft basically owns. And then what Microsoft said is, you know what, if we get into this atmosphere, if we get into this game of providing the overall infrastructure, we can put deals together that lower the cost of one and the other, but we grow the entire enterprise footprint. So we can do mega deals. And that's what basically Microsoft has done, and they're growing the fastest out of all of them at the moment. Amazon just makes it really, really easy to choose every single thing you want. Google doesn't have as many options and not as many enterprise customers use it. However, for a few things that they do have, they own, for example, TensorFlow. TensorFlow is the most robust mathematical package working on top of what are called graphical processing units, which are just like a type of chip that's specialized for machine learning, and they have the best version of that. So if you want to do something really special, Google, you want to just get started, like if we were all doing a startup, we probably go to Amazon. If we're a big company, we want to go to public cloud, probably go to Microsoft. But the point is, yeah, all these different things that you want to, no matter what it is you're trying to do, you can probably do it on here. Back to your question earlier, though, Apostolos, if you were going to be a solo entrepreneur, a solopreneur, as I mentioned at the very tail end of the video I sent to you all yesterday, you probably don't need most of any of this. You probably need WordPress, maybe a Shopify website where they let someone else handle all the back end of whatever it is that you're wanting to do. And you focus exclusively on getting in front of the customer and spending all your time on that. You don't need to spend all your time learning all the back end. If you want to do this, switch your master's degree, go somewhere else, and go start studying this. Or even better, go on Udemy and take some classes for a couple $100 and get the certifications. All right. All that being said, everything that we talked about, it sounds really, really complex, right? It sounds like this machine learning code, and to get through these, those first little red circles that Björn was silently making fun of, to the yellow circles, to the blue circles, all the code that goes into that, it sounds very complex. The math sounds really complex. Finding the library sounds really complex. It sounds like that's like a ton of work, right? And so if we were in a big company, like that must be all we're doing, right? We must just be spending all of our time just thinking about and doing that, right? Surely that's the case. Well, it's not the case. This is a picture that came from Google, a Google Scholar, you can find it on Google Scholar, but it came from a Google research group that basically, you'll see this chart if you ever go to nerd conferences all the time, but the machine learning code is the smallest portion of the overall tech stack. When you build something, you accumulate a term that's called tech debt. And what that means is, let's say we're all launching a startup and we want to get started really fast, right? Because we have an idea and we're like, we need to get that idea really, really quickly out, because those seed investors, those angel investors that we talked about at the very beginning of classes, they want to see that idea not on a PowerPoint slide. They want to see it in some minimal viable product as quickly as possible. So we got to really, really quickly do that. And it can't be just having a wired up diagram that shows if we click here, it goes to here, and blah, blah, blah. We have to actually show it working with some data. We have to show it doing some output. We have to show that a couple of initial users like it. So we have to actually build something. And as we build that, we're going to take, usually, like I said, we're all engineers and developers, right? We're going to take the shortest distance between between idea and product. And as we do that, we're going to make some trade-offs. We're going to say, well, if we were to engineer this the way that the software engineer, as I mentioned earlier, does, software engineer is not going to do this in a very just get the damn thing out the kitchen kind of way. They're going to say, well, how can we do this in a way that's going to scale here? It's going to be so secure here. That's going to be able to work across these different platforms. It's going to be within these standards and blah, blah, blah. Those are really important considerations to have later. But right now, we just got to get the thing built. And in order to get the thing built, we're going to make some trade-offs that are probably not going to be good for the software engineer, and the software engineer is going to hate us for having done. And that is called tech debt. We accumulate debt, technical debt, that we have to pay off later. And so the product is a constant struggle between the product side and the engineering side of build the thing versus build the thing to scale. This takes a lot of time. This is really fast. This does something really efficiently. This just gets it done, right? So inside here, you have the whole point of this chart is to say that getting the code done, by far the smallest portion of the overall pie. getting the code done and then trying to get it tied together with an overall platform, where how are you going to collect the data? How are you going to configure all the things that you're working on? How are you going to extract those features? Remember, like our picture of George Washington? How are we going to extract those features on a regular basis? And that's not just done for visual analytics. We do feature extraction for stock market patterns. On you have features on high, lows, buy, sells, volumes, et cetera, et cetera. You can do it across anything where there's data. Especially over time. How are we going to verify that data? How are we going to manage the resources? Like I said, with Dockers and containers, Docker containers and Kubernetes. How are we going to provide the right tools? So, like I said, with our databases and our, Python, and using notebooks and the libraries and dependencies that they're going to have. And by the way, you can get started with those things for free, but once you get to an enterprise level, there's a lot of cost that goes into it. And companies are going to come in and say, well, you can have this, but you can't have that. So which analysis tools are you going to need, and which ones are you going to be able to get? And are there trade-offs between those? To the process management, how are you going to continuously improve, continuously develop, the CI/CD pipeline? To all the infrastructure that's going to make it work, right? Everything we talked about here from the Amazon Web Service, if you're doing like an interactive type of tool, versus if it's just something really simple and it's a blog post, man, it's a lot easier. To then how are you going to monitor it and keep this whole thing going? So there's just like a ton of considerations that if you don't have those things in place, your code, again, is just going to sit on your laptop. You're going to hire someone from somewhere to come in and build up this really cool model. You provided the data on it, but it is not sitting on some infrastructure. It's not sitting as a part of an overall framework that you can apply to your application that you can go sell to other people. Big problem. So with all that being said, let's just skip past this last one because this was just talking about all the skills. Kind of a puzzle list goes back to some of the questions you were asking earlier, like what do I need to know? This is data science specific. I don't think any of you really want to be a data scientist. So let me just kind of wrap this back together from venture capital, entrepreneur, changing the world kind of perspective. You have, assuming that you are not wanting to become a specific data scientist or a data engineer or a machine learning engineer, or you want to develop infrastructures and architect these types of solutions, then why do you care about this as a finance student? Why do you care about this as an investor? Why do you care about this as someone who's going to go work in M&A or trading or in consulting or whatever? The reason why you care about this is because even if you're not in one of those roles, it's going to have a massive impact on your life. And being educated about how all this works, and after this 90 minutes that we've spent listening to me just talk nonstop, you probably know more about this, even though you probably are like, I don't understand a word he said. You at least have been exposed to more about this concept than easily 98 to 99% of the population. Easily. That is power. Knowing what AI ML is, knowing what data science is, knowing how it comes together, knowing what infrastructure is behind it, knowing all those things is power. It gives you power to go into interviews. It gives you power to go into meetings at work. It gives you a power advantage over the people who don't know it. The second thing is, the more you read on this and the more you understand it, and the more, to Apostle's question earlier, there's tons of people who are working on this. There's tons and tons of folks who are trying to solve an infinite number of problems. And there's no way I can know it all. You don't have to know it all. What you have to know is kind of like a machine learning algorithm. You have to know just enough to start identifying the patterns, to start being able to see the features of the landscape of what you're working on, to start to see, well, I kind of see that there's a big problem on how this is working in enterprise, or I see a problem with how consumers are not being able to get this data. And as you start seeing those problems, you start seeing ideas of, okay, well, I see how that problem could be solved conceptually. And I know the type of person I need to find on LinkedIn to go have that discussion with. Hey, I need to go talk to, actually, I need to go find a data engineer. I'm going to go to LinkedIn, data engineer, I type it in, and I find someone who's a data engineer who has been working on this type of stack. I reach out to them. Hey, I see you're working on this. I would love to just have a 30-minute conversation with you. I'll send you some Vimo, some money for coffee if you'd be willing to have that chat. You start having that chat, and then you're starting to understand, well, how can we specifically solve this problem? Maybe you have someone who wants to come join you in solving the problem. And then you start getting down to GitHub because you know where to go and collaborate with people on these types of issues. You have an idea of what type of software stack you're going to need. You have Dad's credit card, so you can go to AWS and set up your initial environment. And now you can start with your software, with your application, solving some problem across the landscape. And you know who to go reach out to from an angel investor. You know what a seed investor is going to look like. You know what type of, how much money roughly they're going to be able to give, what they're going to be able to provide you, what you're going to get out of it from a cap table perspective, how long that should be able to give you a runway for, and it should be at least get you to a Series A, what a product market fit should look like, and will you get enough customers to get to a Series A, and so forth. That's kind of how the whole thing comes back together. This isn't to teach you to be a data scientist. It's not to teach you to be a machine learning engineer. It's not to teach you to be a technologist around all the different things that are here. It's to give you a very, very big holistic picture of when you walk out of this class today and you take off and you get a lunch, look left, look right, and realize that whether it's in your hand, in your pocket, as you're walking through the store, there are an infinite number of things where someone stepped up and said, I know that there's about a 20% chance that I'm going to succeed in doing this. There's an 80% chance I'm going to go bankrupt and fail at doing this, but I'm going to try. And whether that is from the first person who said, I need to wake up in the morning and I'm going to create an alarm clock, to the person who created the smart light for the bedroom that's going to automate, you know, the right level of lighting, to the person who's predicting what time I should wake up based on my fit tracker that says, I know that I need to have this much rest because I've spent this much time on the bike. And however, the world is going to continuously evolve from the most rudimentary to the most advanced. And now at least you have a perspective of how all those pieces come together, and you can start double clicking on each of those areas and go get a little bit smarter. So like I said, I'll do you the favor. I'll go back and try to make a couple of shorter videos around these. And I also, in one of our next classes, we will start talking about specific startups in this landscape. So now you know the landscape, you know it's kind of like massive big picture problems. We'll start talking about specific startups there, and then we'll let you guys choose which one, if you guys wanted to be a startup team, you wanted to represent one of these startups. And all the information is going to be there for you. You have their websites to go look through. You have all their public information available. And then we will start working together on kind of coming toward the January timeframe where you will present if you are a Datadog or if you're a Snowflake or Databricks or whatever, and you'll be able to present the problem you're solving, the size of that problem, the growth of that problem, and why we, as everyone else in the class, should invest in you in solving that problem. All right, we're over time, but I will hang for any questions that you have, and I appreciate your patience. All this. Let me grab some water. Thank you, Theodora. They need a German version where you like knock on the glass. Really, anything. You can just ask me what I think about anything right now. Does Professor Ernst still wear a three-piece suit to class? Does he still wear like the full suit with the tie and the vest?
We don't have lecture this semester with him, so.
Oh, really?
No.
Have you guys ever had a lecture with him?
Once we had, I think last week or 2 weeks ago, we had one lecture. That was the only one in this semester.
How long was it? He usually goes for like a few hours.
Was it 3? I'm not sure.
Oh, that's brutal. Pack a lunch. Yeah, he did a 3-hour one for us one time, and one second.
Last semester, I think we had like 4 to 5 hours with them, didn't we?